Bismillah Rahman Rahim. In first part of our Bligh theory lecture, we have studied that how we will develop the criteria to be for the impervious floors to be safe against piping and to be safe against the uplift. So we have in that video, in part 1, we have derived how you will find the length of the impervious floor that will be safe against the phenomena of piping, and how much should be the thickness of the floor, impervious floor thickness at various points so that it should be safe against the uplift. So today we will try to calculate that for a particular hydraulic structure, how long it should be the length of the impervious floor and what should be the thickness of the floor at various points. So if you haven't seen the first part of the video of Bligh's theory, please go there and watch that lecture, so then you will realize that how we have derived to these formulas for length of the impervious floor and the safe thickness of the impervious floor. And then in today's lecture we will try to solve some numerical problems so that you can practically use the concept of Bligh's theory for the design of impervious floors. So now here's the first practical numerical problem of design of length of the impervious floor. So a barrier impounds 5 meters depth of water on its upstream. So this is the barrier. Barrier means it could be a weir. Let's suppose it's a weir, and the impounded water is 5 meter on its upstream. The structure is built on a sediment with the value of C as 6. So the C value is 6 for the subsoil. What that C value means, we have studied in detail in the first part of our Bligh's theory lecture, and C is different for different soil types. And is please provide an impervious floor to resist the piping failure. So the task is to provide a piping sufficiently long floor so that it is safe against the piping failure. So we have studied in the first section of this video that the length of the impervious floor L is equal to C multiplied by H. Here C is 6 for the sediment on which the structure is built, and the depth of water is 5 meter. So the length of the impervious floor should be 30 meter. So here, this is the illustration. You can see you have to provide a horizontal floor of 30 meter length so that it is safe against piping. Now in the next section of the video we will study that it is because it is costly and difficult to build a horizontal floor of 30 meter length for the whole hydraulic structure. So that's why now we will learn how to provide the sheet piles, and if we provide the sheet pile at the upstream or at the sheet pile at the downstream, how it will affect the thickness of the floor, and how it will which option will be better to provide the sheet pile at the upstream of the structure or the sheet pile at the downstream of the structure. This is the upstream and this is basically the downstream of the structure. So now in the previous section we have found that the length of the impervious floor should be 30 meters so that it should be safe against the piping failure. So now there could be different cases. So I have illustrated 3 of the possible cases. There could be further more cases also. So here you can provide a horizontal impervious floor of 30 meter length, right? It is safe against the piping failure according to the Bligh's theory. Then there is another scenario. Here you can provide a sheet pile at the downstream side of depth 4 meter, and then you have to provide a horizontal floor of 22 meters. So the water, according to the second assumption, the water seeps or creeps along the base profile of the structure. So 22 meter plus 4 and 4, 8 equal to 30. So it also fulfills the condition of 30 meter impervious floor. Now In case 3, you can see we can provide a sheet pile at the upstream of 3 meter depth and sheet pile at the downstream of 4 meter depth. So here again, water seeps along the base profiles of the structure. So 16 meter we have to provide the horizontal flow, and the remaining will be in terminal of the sheet pile. So again, this fulfills the condition of 30 meter impervious floor lengths. So in all these scenarios, our impervious floor is safe against the phenomena of piping. But now there could be a question, why we are providing the sheet pile at upstream and downstream, here in this case only at the downstream, or there may be a case where you provide only at the upstream. So why we are doing this, or which one is better, or what to adopt? So this will affect the position of the sheet pile, will affect the thickness of the impervious floor, because let's say in this case we have studied in the first part of the video that according to the second assumption that the hydraulic gradient will remain constant. In this case the hydraulic gradient is H over L, which is 5 by 30, which is 1 over hydraulic gradient is 5 by 30. So the hydraulic gradient is 1 over 6. So it will remain constant. So now what will be the profile of, I will try to make it with red. So how the hydraulic gradient, it will be a constant. I haven't, like, let's say, it will be a constant line. It should be a straight constant line. So because there is no sheet pile in this case, what will happen in this case? There will be a head loss due to first sheet pile, then it will go there, and then there will be again a head loss due to this sheet pile. What should be the value of the head loss? We have studied in the first part of the video. In this case, what will happen? It will go like this, then this part. This should be the straight. So this is the head loss due to this particular sheet pile. Now we need to understand that we have studied the length of the impervious floor, but going in the direction of thickness of the floor, at upstream the thickness could be a paper thick, like in a millimeter thickness thick of impervious floor is safe against the phenomena of uplift. Why? Because there is an uplift force, and here is a counter force of impounded water. But when you go to the downstream side of the section, there is no counter force. There is no counter force of water. So at the upstream side, you can place only a paper thick impervious floor. It will be safe theoretically against the phenomena of uplift. But at the downstream section, you have to provide a thickness of the floor according to the Bligh's theory formula of thickness, which we have studied in the first section of this video and derived in the previous part of our Bligh's theory lecture. So here you have to provide the thickness of the floor. So now let's say this residual pressure is no concern for us because it is counterbalanced by the water. So we have to provide the floor thickness for this residual pressure in this case. So let's say here, if we provide the sheet pile instead of downstream at the upstream, I provide the sheet pile here. So what will happen? Now there will be head loss here, and it will go like this. So now you see the residual pressure, which is responsible for the uplift, is lower in the downstream section. So if you have to provide a single sheet pile, you have to provide at the upstream because it will reduce the uplift pressure head at the downstream side of the hydraulic structure. So what will be the benefit? That you have to provide the comparatively less impervious floor thickness if the sheet pile is at the upstream. We will also study a practical numerical problem now to find the floor thicknesses at different locations, at different points on the upstream and downstream sides of the impervious floor. Bligh said that even if a paper thick impervious floor is safe, but you have to provide a nominal thickness. And what he suggested that in case of thickness, and the point is at the upstream of the hydraulic structure, so at least we have to provide 0.4 meter thick impervious floor. So now we will study one practical problem, and then the things regarding the thickness of the impervious floor will also get cleared. So now this is a practical example of to find the impervious floor thickness at various points. Here in this structure, this is a barrier. Let's consider it a weir. So the seepage head at the upstream, the depth of the impounded water is 5 meter. So H is given as 5 meter. There is a sheet pile at the upstream. This is basically the upstream, and this is basically the downstream side. I will just put it downstream. So here is a sheet pile at the upstream of depth 5 meter. Then there is an intermediate sheet pile of depth 2.5 meter, and then there is a downstream sheet pile of depth 10 meter. Then your task is to find the depth of the thickness of the impervious floor at point A, which is at the upstream of the hydraulic structure, at point B, and at point C. Point B and point C are at the downstream of the hydraulic structure. Then the distances, horizontal distances from upstream sheet pile to point A is 5 meter. From upstream sheet pile to intermediate sheet pile is 10 meter. From upstream sheet pile to point B is to intermediate sheet pile was 8 meter, and to point B was 10 meter, and now the total horizontal distance is 20 meter, and between point B to C is 5 meter. So when we, in our first task is always to find the creep length, which we have studied in the first part of the video. But how to find the creep length? We have studied that the water will seep along the base profile of the hydraulic structure. So this thread, if you stretch this thread, it will be a straight line. So now the horizontal distance 20, and then you have to add all the vertical distances of the sheet pile. So 5 meter this and 5 meter this, 10, 2.5 and 2.5 upward direction, 5 and then 10 and 10. So it's a 20. So we have taken the two common, 5 plus 2.5 plus 10, and total is 25. Now we know the seepage head at the upstream is 5 meter, and the hydraulic gradient is always like the seepage head divided by the total length, or in our case it's a creep length, so it is 1/11. So now up to this point we have found the length of the creep and the hydraulic gradient, and we are familiar the value of the seepage head is given, which is the 5 meter. Our task is to find the thickness of the impervious floor at point A, at point B, and at point C. So now we are at point A. So first thing, and we know the total creep length is 55 meter, and our average hydraulic gradient is 1/11. So what we did, we find the length of the creep. Now our aim is point A, so we have to find the creep length only up to point A. So it's a 2 times 5 plus 5, so it is 15 meter. So now uplift pressure head is always hydraulic gradient, average hydraulic gradient, into total creep length minus the creep length of the point, which is now your desired location where you want to find the length, the thickness of the impervious floor. So the total creep length is 55. The creep length up to point A is 15, and the hydraulic gradient is 1/11, and you'll get 3.63 as a uplift pressure head. Now uplift pressure will be uplift pressure head multiplied by the specific weight of water, which is 9810. So you will Newton per cubic meter, and you will find the answer of uplift pressure as 35610 Newton per meter square. Now we know the thickness of the impervious floor is 4 by 3 into h over g minus 1. So here our 4 by 3, h is 3.63 meter here, g is 2.24 for the concrete. You can find it from literature, and its value ranges from 2.24 to 2.4. And now this minus 1 will come. We have lastly studied that why we did this minus 1 while we were driving this formula. This was due to the submerged weight of the impervious floor. So you will get the floor thickness of 3.9 meter. But as I have explained in the first section, in the previous section of this video, that as this point is on the upstream of the hydraulic structure, so you need not to provide a thickness of 3.90 meter, because it will be then the wastage of money. Because to counter the uplift force, there is a impounded water, so the structure will be safe. So even you can put a 1 millimeter thickness impervious floor theoretically. But the Blighs have provided the criteria that if a point is at the upstream, you have to provide a nominal thickness of 0.4 meter. So I would have said that you can, if it is upstream, you could provide only 0.4 meter. But I have explained it here that this formula thickness will provide the thickness of the floor at the downstream points on the hydraulic structures. For the upstream points, you have to provide the nominal thickness of 0.4 meter. So now, let's say we find the thickness of the floor at the point B. So we go to here, point B. So now here, so what should be the length of tube up to point B? So you can see 5. This will go now from here, here, here. So point B. So you can see the horizontal distance up to point B is now 10, plus you will add 2.5 plus 2.5, 15, and then 5 and 5, 10. So it will be like 25 meter. So now, in case of uplift pressure head, here it will be now IB. So our average hydraulic gradient will remain constant. So total creep length will remain constant, and here it will be now 25. So our answer will be now, in case of point B, 2.72 meter. So this is our uplift pressure head at point B. So now we have to find uplift pressure. So this will be now 2.72 multiplied with the specific weight of water, and the answer will be 26683. 26683 Newton per meter square. So now, while solving this formula, we have to now update the values. So our head is 2.72, and G will remain constant, 4 by 3 is constant, and our thickness comes out to be 2.92 meters. So here in this case, at point B, we have to provide the thickness of 2.9 meter at point B. So it is 2.92 meters. So now let's say we move towards the point C. So now for the point C, here at point A it was 0.4 meters. So now at point C, what you are supposed to do, in case of point C, now the creep length up to point C we have to calculate here. So up to point C, the horizontal distance is 15 meter, and you will add 2.5 and 2.5, which is 15 plus 5, it is like 20, and then 5 and 5, so it is 30 meter. I'll take another color like. So we have found the length of creep up to point C is now 30 meter, and now we are calculating the point number C, thickness of the flow. So next, when we calculate the uplift pressure head, you just have to, here at point C, and now it's not 25 for point C, it is 30 meters. So you will get an answer of 2.27 meters. So for point C, your uplift pressure head is 2.27 meter, and for that uplift pressure head we will find the uplift pressure. So you now have to multiply 2.27 with 9810, the specific weight of water, and you will get the answer of 22268. And when you will insert this value here, 2.27, and the G will remain constant, the other things are constant, and you will get the floor thickness of 2.44 meters. So now we have found the floor thickness of 2.44 meter at point C. So this is how you will find the floor thicknesses at the each point of the hydraulic structure's impervious flow. So hopefully you have understood the concept of Bligh's theory in order to design the impervious floor to be safe against piping and to be safe against the phenomena of uplift. So there are some also the limitations that the Bligh's mainly limitation was that the Bligh haven't made any distinction between the horizontal creep and the vertical creep. Like this part of this path which is traversed by the water particle is the vertical creep, and this is the horizontal creep. So he said that both will dissipate the head in a similar pattern. Like he didn't make any distinction. Later on, Laney made the distinction between the horizontal creep and the vertical creep. So this was basically one of the limitation, and he didn't explain the idea of exit gradient, that safety against undermining cannot simply be obtained by considering a flat average gradient, but by keeping the gradient well below critical. So he said that the gradient is like flat and constant. So this was basically and he also didn't provide any corrections due to floor thicknesses. So then the Khosla theory has provided these upgrades to the Bligh's theory. Now still there are some limitations, but still most of the small hydraulic structures the impervious floors are being designed in the subcontinent by the Bligh's theory, and if there are larger structures, then we normally move to the Khosla's theory. So hopefully you have understood the lecture, and if you like the content and if you think that you have understood the lecture, please like, share, and subscribe to my channel so that it will support me to make the new videos more oftenly. And I'm also working on the research topics like how to check the plagiarism. I will also try to upload the basic research stuff for the bachelor students, like how to use Mendeley in some of the upcoming videos, and we'll try to also cover the fluid mechanics, irrigation engineering, and engineering hydraulics lectures too. So thanks for watching.